Hello friends, welcome to thesitzer.com. In our last video we learned how alkanes undergo the free radical substitution reaction. From alkanes we can replace a hydrogen atom by a halogen to get alkyl halide. So from here we can get alkyl halide plus halogen acid. This is a free radical substitution reaction where you replace a hydrogen atom from the alkanes with a chlorine free radical. The mechanism part we have done in our last video, how this reaction actually occurs, what are the steps in it. Now we will learn about the reactivity of the halogen molecules towards a particular alkane. The reactivity of the different halogens towards a particular alkane here in this reaction follows: fluorine the most reactive, then the chlorine, then the bromine, then the iodine molecule. So this is the fastest and this is the least one towards a particular alkane, towards a particular hydrogen atom. This is because the free radical, the fluorine free radical, it takes the hydrogen, it abstracts the hydrogen from the alkane very quickly, and the order of the hydrogen abstraction is this one. Fluorine free radical the fastest one and iodine the least. If we take this example here, ethane, and react with the chlorine and heat it or use the high energy radiations, the free radical substitution can occur from this carbon or from this carbon, right? So we got the two carbon atoms, but from either it goes the substitution from this one or from this one, you always get one product, chloroethane, because the two carbon atoms are equivalent. However, molecules like propane, from here we get two types of products, because we got a primary carbon here, this is also the primary carbon, but while at the central one this is a secondary carbon. If the free radical substitution occurs from this carbon or from this carbon, you get the 1-chloropropane. From the central one we get a 2-chloropropane. That means when we do the halogenation of higher alkanes, propane or higher members of the alkane, we will always get a mixture of the products. Now in this video, in this lecture, we will learn about how to find the percentage of these products, right? How we can calculate the percentage of the 1-chloropropane and 2-chloropropane. But before that, let's have a little bit idea about the reactivity of the primary and the secondary and tertiary hydrogen atom. Secondary hydrogen atom is always more reactive than the primary one. It's like this. Propane, we got the secondary carbon, so it has a secondary hydrogen atom attached there. You got here the primary one, here also a primary one. The secondary hydrogen is more reactive than the primary hydrogen. That means the substitution will occur more readily at secondary one than the primary one, because the free radicals that you will get from the primary and the secondary will be, so from the primary one you get the CH3, CH2 free radical. Okay, so once hydrogen is abstracted from here, from the primary carbon, you get the primary free radical. If the hydrogen is replaced from the secondary one from here, the free radical will be a secondary free radical, which is more stable. We know the order of stability of the free radicals. Tertiary is more stable than secondary than primary. So here in this case, a secondary free radical is more stable. This is more stable free radical, and this is the less stable. That's why hydrogen abstraction from the secondary carbon is more easy than from the primary one. So we get a conclusion: secondary hydrogen atoms are more reactive than the primary ones. Similarly, tertiary hydrogen atoms will be more reactive than the secondary ones. right? Again, because the tertiary is more reactive, tertiary is more stable free radical than the secondary. So if you get a molecule like this, suppose we got this one, CH3, CH3 here, then the CH2, and this is the CH3. We see here this hydrogen is a tertiary one, and this hydrogen here from this carbon is the secondary one. Okay, when you replace the hydrogen from the tertiary, you get a tertiary free radical, from the secondary you get a secondary free radical, and from these carbon atoms you get the primary ones. And the stability order is always tertiary is 300 degree free radical is more reactive than secondary than the primary. This is the order of stability of the free radicals. Tertiary free radical is more reactive, more stable than secondary, which is more stable than the primary. So that's why the tertiary hydrogen will be easily replaced than the secondary than the primary. So let's take an example of a chlorination of alkanes. In chlorination of alkanes, the order of reactivity of the hydrogen atom is tertiary is more reactive than secondary than primary, and in chlorination the order is 5:4:1. So let me explain it here with an example. That means if you got a compound that has a primary, secondary and the tertiary hydrogen atoms, so this is the secondary one and this one is the tertiary one. Here this is the tertiary free hydrogen atom, this is the secondary one, and these three are the primary ones, right? These are the primary ones. So chlorination of this molecule or any alkane follows the order of 5:4:1. That means tertiary hydrogen is more reactive than the primary hydrogen 5 times. Okay? Tertiary hydrogen is more reactive than the primary hydrogen 5 times. Is 5 times more reactive than the primary one. So tertiary hydrogen is 5 times more reactive than the primary hydrogen atom. Okay. Similarly, we can say a secondary hydrogen atom is 4 times more reactive than secondary hydrogen atom is 4 times more reactive than the primary hydrogen atom. Okay, and overall chlorination of alkanes follows tertiary is 5 times primary and secondary is 4 times the primary. So overall order is 5:4:1. This is the order of reactivity of the tertiary, secondary and the primary hydrogen atoms. So now let's calculate the percentages, right? Okay, here we got, this is the alkane, contains a tertiary hydrogen atom and primary hydrogen atoms, right? We got the tertiary and the primary. When we do the chlorination, you get this one and it's only 36%, right? And when you do the chlorination from the primary one, you get 64%. But we learned that tertiary is more reactive than primary. Okay, tertiary is more reactive than primary, and it is 5 times more reactive than the primary one. That means we should expect the ratio should be 1 primary and 5 times this one, right? It should be the other way. But what we find it is the primary one is more, it's 64%, and the tertiary is only 36%. This is the experimental ratio. This is what actually you find. This is the actual ratio, 64% primary and 36% here tertiary. Why is it so? So how do we calculate actual ratio? We calculate from the number of hydrogen atoms. See how many hydrogen atoms are here? 9 primary and 1 tertiary. So as per the number of hydrogen atoms, the expected ratio should be 9:1, right? 1:5 is the expected ratio as per, this is the ratio expected as per the reactivity. Okay, this is the ratio that we can expect as per the reactivity of the hydrogen atoms. It should be 1:5, because we know chlorination, in any case chlorination of alkanes, it follows tertiary hydrogen, secondary hydrogen and the primary hydrogen. The ratio is 5:4:1, right? We know it. And therefore the expected ratio should be 1 primary and 5 times tertiary. And from the number of hydrogen atoms, you can see there are the 9 primary hydrogen atoms, right? So from the number of hydrogen atoms of primary and the secondary, the expected ratio is 9:1. However, the experimental ratio is totally different. The reactivity not matched with the number of atoms. So how do we actually calculate the percentage? Okay, so we can calculate the percentage of the primary one. From the primary one, let me say it is the molecule A. If the substitution occurs on the primary one, the compound A will be produced, and if the substitution occurs on the tertiary one, and the compound B will be formed. So what is the percentage then of A and the B? Then we can say the tertiary one, if substitution occurs on the tertiary hydrogen, we get the compound B. And what is the percentage? Let's calculate that. We calculate it by taking the number of hydrogen atoms of the primary and the tertiary here. So how many primary hydrogen atoms are there? There are 9 primary hydrogen atoms. And what is the order of reactivity? Multiply the order of reactivity, it is 1. So what do you get the total? 9. Okay. How many tertiary are there? There is only 1 hydrogen atom. 1 tertiary in the molecule. Number of hydrogen atoms is 1. Okay. Multiplied by the reactivity order, and that is 5. What do you get? It is 5. What is the total value here? 9 plus 5, it is 14. Right? 9 plus 5 is 14. So the percentage of A will be then equal to 9 upon 14 multiplied by the 100. 9 by 14 into 100, the total here, right? Into 100. That comes 64%. Okay. So the for B will take 5 by 14 into 100. So you get 36%. This is exactly the same ratio that we get from the experimental ratio. Okay. So we actually take both the factors, right? So there are 2 factors actually that can determine the ratio. Not only the number of hydrogen atoms, you can see from the number of hydrogen atoms we can expect it should be 9 times more than the primary one. But as per the reactivity order, the tertiary should be 5 times more than the primary. But the actual order is the combined effect, right? The combined effect of the reactivity and the number of hydrogen atoms, right? Reactivity here 5 and number of hydrogen atoms is 1. Okay, and then get the relative ratios. Let's take one more example to find the percentage. From here, from this molecule you can see we got a primary hydrogen and a secondary hydrogen, right? We got the 2 products. From the primary one you got this 1 chloro, from the secondary one you got the 2 chloro. Now let's find the percentage. What percentage we can expect there? So let's say this is the compound A and this is the compound B. Then the compound A, which is formed from the primary one, right, isn't it? This is formed from the primary one. So primary one, it is, how many primary hydrogen atoms are there? There are 3 plus 3 is 6. And what is the order of reactivity? For the chlorination, we know that chlorination always follows the order 5 is to 4 is to 1, right? Remember this order. This is for the chlorination. For any alkane, right, when we do the chlorination, 5 times, tertiary hydrogen is more reactive than secondary, then primary, and the order is tertiary is 5 times, 4 times secondary, and primary 1. So here the number of hydrogen atoms is 6 in this case, and the reactivity of the primary hydrogen atom is 1. So the total is 6, right? And the B will be 2 hydrogen atoms are there. The order of reactivity is 4. 4 into 2 is 8. 6 plus 8, it is 14. And what is the percentage? Let's calculate the percentage of A. Percentage of A will be calculated by dividing the 6 here, this 6 value, by 14. 6 by 40 into 100. 6 by 14 into 100, it is 43%. And for the B, it will be 8 by 14 into 100, which is 57%, right? So that means you get A 43% and B will be 57%. Let's take another example. This particular compound, you can see here a number of compounds, as a number of hydrogen atoms. You can see here different types of primary. This one and this one, it produces the compound A, right? So if substitution occurs over here and here, say this is the compound A, and let's say this is the compound A, right, when we do the chlorination. And if tertiary hydrogen here, this one is replaced, you get the compound D, right? So this is the compound D. When substitution occurs on this one, this is the secondary one, you get the compound C. This is the compound C. And if substitution occurs over here, you get a primary one. But this primary is different than these two, right? These two, they give, they produce the same molecule, but here from this one you get a different one. So you get the compound B. So overall, from this molecule, when we do the chlorination, we get 1, 2, 3, 4. 4 different products, right? So we're going to calculate the percentage of each compound there. And again, for the chlorination, we know the order of reactivity. What is the order of reactivity? Tertiary is, tertiary, secondary, and the primary. What is the order of reactivity? It is 5 times 5 is to 4 is to 1, right? 5 is to 4 is to 1. Fine. So now let's find the percentage of A. So what will be the percentage of A? So you got the 6 A primary hydrogen atom in there, right? From A, 6. Number of hydrogen atoms is 6. And the order of reactivity of the primary is 1. So it is 1. So it's 6 into 1 is 6. Right? What is the percentage of B then? So B here, you can see this is the primary one, this is another primary one. There are 3 hydrogen atoms into 1. Reactivity is 1, so it is 3. C will be equal to, so C is the secondary one. You can see the secondary one, okay? Secondary one. There are 2 hydrogen atoms there. So number of hydrogen atoms is 2. Reactivity is 4. So 6 into 4 it is 8. Sorry, 2 into 4 is 8. And the D, molecule D will be, it is number of tertiary, it is 1. The order of reactivity is 5. Okay. So 6 plus 3 plus 8 plus 5 the total, what's the total here? It is 22, right? 22. Then what will be the percentage of each compound? What is the percentage of A? How we calculate it? Divide the 6 by 22 and multiply by 100, right? 6 by 22, 6 by the total value here, that is 22, into 100, you get the percentage. And for the 3 one, it will be, for the B it will be 3 by 22 into 100, right? And for C it will be 8 upon 22 into 100, and for D it will be 5 upon 22 into 100. And we can calculate the percentage of different compounds. Here this one is 27%, and 3 by 22 it is 14%, and 8 by 22 into 100 it is 36%, and 5 by 22 into 100 it is 23%. So we got the percentage of the different compounds here. Hope you got the concept. Thanks for watching the video. Bye for now.